Okay, so for 13 and 14 and 15, I'm only going to do the examples that are important for the homework. Um, and of course, test problems will come from the same subject matter. So if I skip a section or an example, that means it's not as important. Plus, we're treating these three chapters as sort of one topic altogether. Especially chapter 15 doesn't have a whole lot in it. Okay, so here's the examples here. So with 13.3. All right, this is a linear expansion problem. So basically, you always have this set up where you have some object, usually it's a bridge, okay, where you have some initial, should have put that up here, some initial length, L naught, and it's going to undergo a temperature change. So between two positions here, and it's going to grow, and this little section here is delta L, so the change in the length. And you have a delta T between the two positions. It can grow or it can shrink, okay, depending on if delta T is positive or negative. Okay, so this problem, well, we'll put the general formula here. Delta L is this alpha times the original length times the delta T. This alpha, I'm not going to write it out, it's the coefficient of linear expansion. That depends on the material. And if we're talking about steel, there's a table of these on page 364. And they're very small. This is in 10 to the negative 6. It's inverse degrees Celsius. Okay. It's steel, so that tells us alpha. Now, the steel bed of the suspension bridge is 200 meters long at 20 degrees. Now, we're looking at the extremes, meaning from negative 30 Celsius to plus 40 Celsius. How much will it contract and expand? Okay, so there's actually, in figuring out the delta T, there's actually two things we need to do here. So, first of all, remember for delta T, it's T2 minus T1. And since we have this L naught, I'll write it here, of 200 meters at 20. So this is important that this is at 20. Then what we can do is do this calculation going from 20 to negative 30, and then do it again going from 20 to positive 40, and that way we get the range, just because this is the information we're told. So we have to start from here and go to the two extremes. So we'll just go ahead and do that. Okay, I'm not going to rewrite out alpha. That's alpha right there. Okay, and then 200 for L naught, and T2 is final. So let's go to negative 30 minus 20. I will say for most of the stuff in this chapter, anytime it's a delta T, you can use Celsius, because delta T in Celsius is the same as delta T in Kelvin. If the T is by itself, you have to use Kelvin. Um, so I want to get the number on this, so I'll go ahead and do the calculation. Okay, now it's times negative 50 for delta T. Okay, I get a 0.12. And I'll just do this again. Now we're going to go, it's positive 40. So that's a 20 degree. Okay, so meters. Okay. So basically, this is going to be negative 12 centimeters, and this is 4.8. Okay, so that's the range. So from negative 12 to 4.8, so that would be 16.8 centimeter range. Okay, next one. $13.9. I'll mention, we're not going to do it, but there's also a volume expansion, which is the exact same thing except you use beta, which is the volume coefficient expansion. Okay, now we're getting into the ideal gas law problems. So I'll also say that you've probably seen this in a chemistry class before, so if you're familiar with this, that's fine. Also, if you have your methods for doing these problems, chemistry type methods, go ahead and use them, or notations or anything like that, go ahead and use what you're used to. I'm going to do it a certain way that follows the book. Okay, so 13.9. Volume of 1 mole at STP, so standard temperature and pressure. And I usually have to look these up even though they're fairly, that's 273 Kelvin is 0 degrees Celsius. And pressure of 1 atmosphere. Okay, now we got to be careful with our units here. So we need Kelvin temperatures and Pascal or newtons per square meter pressures. Okay, so determine the volume of 1 mole of any gas, assuming it behaves like any ideal gas. That means we can use the ideal gas law. So this is about as straightforward a problem as you can get. Okay, so pressure, volume, number of moles, gas constant, and temperature in Kelvin. I'll write down the gas constant. This should have that number available. So we're solving for volume. So there's nothing more to it. Just at this point, just plug everything in and get your volume. Okay, 13.10. Helium balloon. So just to see what else we can do with this ideal gas law. So this helium balloon, it's a sphere, radius 18 centimeters, at room temperature, and that's 20 degrees Celsius, and 1.05 atmospheres. Find the number of moles of helium in the balloon, and the mass of helium needed. And the only thing different here is you have to apply the volume formula for a sphere, and then solve the ideal gas law for N. So I'll leave it at that. Now mass, to go between mass and moles, you need to take the number of moles, whatever you got here, times the molecular mass, which is basically, I think it's the atomic mass number of the element, meaning, for helium, that's, this is where my, I'm not a chemist, okay? So when this edges into chemistry, I sort of have some mental blocks that get on me, but this is 4 for helium, meaning 2 protons and 2 neutrons. So whatever you got here, just times 4, and that's those numbers are grams per mole. So just multiply through. Okay, 1312. Okay, now this is sort of a variation on the ideal gas law, which basically, and I like this part of it. So this, what we calculated here, as long as the number of moles don't change, then this is a constant, and this is a constant. Okay, so for any one system, as long as you don't add or take away gas molecules between 2 steps, you can go from one state to another state, and this N is constant, so, and you're probably familiar with this as well. you can set this equal. Okay? It's that combination of, is it Boyle's law, Charles's law, and what's the third one? I never remember that one. Anyway, this is the overall law where for each of those individual laws you can say, well, if the temperature doesn't change, then T's go away. T's are constant, or V is constant, or P is constant. Okay, so for this problem, we're filled, let's see, the tire is filled to a gauge pressure of 210, so that word gauge is important there. But if we're going to start at point 1, let's see, 210 kilopascals. Now it says gauge pressure, which means you have to add atmospheric pressure to this. It's kind of a tricky, it's not as important to me, but it can result in an incorrect answer here. Let's see. I shouldn't need a calculator for this. 311 times 10 to the third pascals. Okay. And see, after a drive of 100 kilometers, the temperature when the tires, this is at 10 degrees C. And basically we're going to raise the temperature of the tire and everything inside to 40 degrees C, and we want to find the new pressure. These are T's by themselves, so not delta T, so you have to add your 273. Let's see, 313. And then we're solving this for P2. Well, of course I'm not solving for V, I'm solving for T. So that where I crossed that out earlier got me. Okay, so P2 is going to be T2 over T1, P1. We're getting warmer. I think I messed that up again. Let's see, P2, yeah, T2, that's right. We're getting warmer, so the pressure should go up. So this T2 over T1 is telling you the ratio by how much the pressure is going up. I can't get my calculator. Anyway, you don't need to see that. 313 divided by 283. Okay, so that ratio is 1.11. So 4, we'll call it 344. That's it. I think these ideal gas law problems are, to me, they're pretty straightforward. It's just paying attention to the details. Okay, so next one is 1312. Okay, now we're moving on. Oh, I just did 1312. Yeah, sorry. Just one more here, 1316. Now this is to a different, this is more back to physics, which is called root mean square velocity. So you take a gas, and the molecules don't all have the same speed, but they have a sort of an average. But it's not really an average. It's called the root mean square, which is a type of average. And we just have the equation to relate this. 3kt over m. This k is Boltzmann's constant. Let's see if If I can find a value. It's very small. 10 to the negative 23 units joules per Kelvin. Basically, this is associating the energy of a single molecule. So that's why that 10 to the negative 23. And so for this problem, okay, speeds of air molecules. What is the RMS speed, which is this, of the molecules O2 and N2 at room temperature? Okay, first K is a constant, so we don't need to do anything there. This 20 we need to turn into Kelvin, so 293 Kelvin. Mass, okay, again, this is going to be the atomic mass number. I don't know the symbol for that. Let's say that was N times the molecular. Again, I don't know the terminology here. The atomic mass unit. Okay, so say for nitrogen, let's do oxygen first. Let's see, 16 protons and 16 neutrons, so that's 32 times, and this is in the front of the book, or you can look this up, 1.66. We'll go to that level, times 10 to the negative 27 kilograms. So basically that's the average of proton and neutron mass. You can see how small it is. We have 32 of them. So okay, so a really small number here, 5.31 times 10 to the negative 26 kilograms. And then we just plug this into the formula. To write out all these scientific notation. Okay, now think about the numbers here. That's a small number, 293 Kelvin. But we're dividing by an even much smaller number, meaning this is a tiny amount of energy, but it's a really, really tiny amount of mass. So usually you get these speeds to be an appreciable number. And don't forget square root. Okay, so I'm getting we'll call that 478 meters per second for oxygen. And for nitrogen, you just do the same thing, except that 32 is going to be a 28. Everything else is exactly the same. Okay, I'll go ahead and stop there.